Hi everybody, I hope this video finds you well. Today we're going to be continuing on from our last video, which introduced the correlation coefficient as a measure of strength of the correlation between two quantitative variables. To go a little bit forward with this, we're going to take a look at another example, sort of work our way through building the visualization, the scatter plot that we've been discussing for a while now, see another example of calculating the correlation coefficient, and then as sort of the moment that'll take us a step forward from what we were previously doing, we'll see what we are able to do if we are able to establish that there is evidence for a relationship between two variables. So this will be sort of officially the video that takes us from simply discussing correlation into discussing correlation and regression. So let's take a look at the example that we have in front of us here. So we're going to suppose that a researcher wants to study the relationship between grade point average and the time it takes for computer science graduates to get their first job after graduating. So what they do is, to study this, the researcher randomly selects 10 recent computer science graduates. They record each of these students' GPAs, and then they track these students until they get their first job. And then they record the length of time it took them to get that first job, and they record that value in months. And so they get this pile of data here. Now, as you can sort of see, again, just as a reminder, each of these sort of pairs of values represents one of these students. So this first pair here represents that the first student in our sample had a GPA of 3.9, and it took them 1 month until they found their first job. This student down here, they had a GPA of 3.2, and it took them 4 months to find that first job. All right, so what are we going to actually do with this sort of data? Well, we're going to start with our sort of basic things. We're going to try to build a scatter plot. Then we're going to calculate that correlation coefficient. And then we're going to use that correlation coefficient to decide if there's enough evidence for a correlation. All three of those things should be identical to what we did in sort of our last example. Now, do keep in mind that before we jump right into building the scatter plot, one thing that we want to do is make sure that we identify the explanatory and response. To give ourselves a little bit more room, we're going to move on to sort of the next page where we'll have the data sort of rewritten. And again, I would strongly recommend, as you guys follow along with this, to write this data down on your own and attempt building the scatter plot, calculating the correlation coefficient, just as we are in this video. All right, so let's give ourselves a little bit more space to work with here. So here's our same data set, right? And the first thing we're going to do is just make sure we identify the explanatory and response. Again, you can almost think about this chronologically, right? The GPA needs to happen before they can start looking for that job, right? They have to graduate before they can start looking for that first job after graduation. So what that tells us is that GPA here is going to be our explanatory, and the months until they find that first job is going to be the response. In preparation for calculating the correlation coefficient using our calculator, we should also put this explanatory data into L1, and we should put the response data into L2. All right. In the meantime, though, we'll go ahead and draw our scatter plot. So let's go ahead and just draw that in here. All right. So again, give yourself your sort of nice quadrant of a coordinate axis. Remember, your explanatory is going to go here, so that's going to be GPA. If we take a quick look, looks like the lowest GPA we had in our sample was 2.8, and the highest was 4.0, so we'll need a scale that sort of shows those. So there's 2.8, and I'll just go by 0.2, 3.0, 3.2, 3.4, 3.6, 3.8, and 4.0. Again, this little section here is smushing in all that sort of stuff from 0 to 2.8. So to remind ourselves of that, we'll put in a little squiggly line there. In terms of the response variable, well, we know that this is months until first job. And if we look there, we see that the lowest value was sort of those ones there, and the highest value looked to be 7. So those are pretty simple values, so we'll just go by ones. 1, 2, 3, 4, 5, 6, and 7. We'll just label those real quick. 6 and 7. Notice there's no need for a squiggly line here because vertically this value down here actually is 0, right? So there's no condensation of that sort of vertical axis there. Okay, so let's go ahead and plot our points real quick. 3.9 and 1, so we've got a data point right there. We also have 4.0 and 2, so we've got a data point right there. Looks like we have 3.6 and 4, so we've got a data point sort of right in there. We have 2.8 and 6, so we've got a data point right there. 3.7 and 3, so it looks like we've got a data point right there. That's a little off. I'll just go ahead and fix that guy. Let's try it again. So that was 3.7 and 3. Looks like more right about there. Then we've got 2.9 and 7. So we've got a data point right there. 3.4 and 3. So somewhere right about there. We've got 3.5 and 2. Right about there. 3.7 and 1. So right about there. And then we also had 3.2 and 4. So right about there. Okay, so there's our sort of data set there. Now, visually, right, again, the thing that we should be able to get sort of immediately from the visualization is whether or not we're seeing sort of a positive or negative direction here. Now, a positive direction means that we're seeing something like that. Clearly not the case here. Negative direction means we're seeing something like that. Definitely seems to be what we're looking at here. So even just based off the visualization, we're sort of expecting a negative direction. That means when we go to calculate that correlation coefficient, we're expecting a negative value for R. And of course, that would sort of generally make sense. If we're expecting that there is a relationship between GPA and the months it takes you to find a job, we would expect that as that sort of GPA goes up, we're expecting these to sort of go down, right? That the higher your GPA is, the quicker you'll be able to find a job. All right. So let's go ahead and actually use our calculator to calculate that correlation coefficient. So what we're going to do is we're going to use that ln reg ax plus b. We already have our explanatory data in L1 and our response in L2, and we will use that and record our R value. So I already have that stuff typed in. We'll just quickly go ahead and calculate that. So what you should get here, if you do this on your own calculator, is you should get an R value of about negative 0.8749. And usually we keep 4 decimals because, as you guys know, that critical value table, the table E, also reports 4 decimals. So just for ease of comparison, we do the same here. So notice that as predicted, we do get a negative R value corresponding to sort of the negative direction. You guys will also notice that this value is, pretty close to -1, so we are seeing a relatively strong negative correlation. Is it strong enough to really say that there's a relationship between these variables? Well, we'll go ahead and use table E here. So if we use table E, remember that with table E, you wanted to know how many data points we had. We have n equals 10 in this case. I'll just scroll quickly to our table here. So there's our table. Remember, we have 10 data points here, and we always use that 0.025 column. So we'll intersect those two values, and it looks like you should be right there at 0.6319. So that is going to be our critical value. So let's go ahead and write that down. So our critical value here is 0.6319. All right, so now we do our comparison. We take the absolute value of R. Remember, this absolute value of R, the absolute value just makes everything positive. It makes it fair, in other words, to compare a negative number to a positive number. So we take that absolute value of R, and how does that absolute value of R compare to the critical value of 0.6319? Well, it should be pretty clear that that absolute value would be greater than the critical value. So whenever your absolute value of your correlation coefficient comes in larger than the critical value, that's saying that the pattern is stronger than that critical or that sort of cutoff value. That means that that pattern we're seeing really counts statistically as a pattern or as a relationship. So we would say there is enough evidence for a negative correlation. In other words, we are convinced here by this data, right, that there is a negative relationship, a negative association, a negative correlation between GPA and the months until the first job. Now, you got to keep in mind, all we are measuring here is correlation. So we are saying that we see a general trend that as GPA goes up, the months until the first job goes down. That is not the same as causation, right? You guys have probably doubtlessly heard over and over people say things like correlation is not causation. And what we're studying here is correlation. So even though we've found enough evidence here, that does not mean that the GPA is causing people to get jobs faster. And that should make sense. If you've applied for jobs before, right, you'll know that looking at something like your school GPA is not the only thing that people are considering. But what this is sort of indicating is that people with higher GPAs might have other desirable traits, and those also are sort of all contributing to finding a job faster. In other words, by determining that there is enough evidence here, we're sort of saying that we're comfortable using GPA to predict when people will get a job, even if it's not directly causing that. All right, so this basically summarizes everything that we've already seen from the previous videos, right? We went ahead and built the scatter plot, we calculated that correlation coefficient, and we used it to determine that there was enough evidence. One thing that's different in this example, though, is that we actually did find enough evidence. In the last one, where we were talking about film budgets and revenue, we didn't find any evidence for a relation, and we ended there. This time, though, there is a relationship. So what can we do with that relationship? Well, it turns out that in statistics, the main thing you want to sort of do when you find a relationship between variables is build a model. Once you know that sort of two things are related, you want to model that behavior so that you can use that model to make predictions, to make decisions, etc. So we're going to talk about a way of doing that. Then, once we've sort of talked about that way, we're going to come back to this example and see what that model looks like in this case. So, to do that, we're going to talk briefly about what's called the least squares regression line. So, the least squares regression line, first thing we should sort of note is this is often abbreviated as LSR. So we don't have to constantly say least squares regression over and over again. We're just going to often call it as the LSR. What the LSR is the LSR is a linear model that attempts to make the best fitting line to a set of, we should put in the word two there, two quantitative variables. Okay, so the LSR is a linear model, meaning that it is a line, right? Linear and line, they just go hand in hand here. So the LSR is a linear model that attempts to make the sort of best fitting line to a set of two quantitative variables. In other words, going back real quick to that sort of diagram, right? If we look at our scatter plot, we can sort of see that if we sort of imagine that there should be some sort of line that sort of roughly fits the data. And of course, I'm just sort of freehanding and drawing it there, but that doesn't look like a bad guess. We know that the line wouldn't be up here. We know that the line wouldn't be here. We know that the line wouldn't look like that. Even just visually, we know that the sort of best fitting line should be somewhere in there. So how do we actually calculate that? Well, that line is called the LSR. Now, the actual mechanisms behind calculating the LSR, calculating the equation of the LSR, are a little messy. They actually come from multivariable calculus, and they're an optimization problem about minimizing the distance between all the points on the line and all your data points. That's way beyond the sort of scope of our class. So luckily, our calculator is able to generate the equation of the LSR for us. So let's just remind ourselves real quick to understand a linear model. We need two things. So if you just think about like when you learned about linear models in an algebra class, right? There's sort of two things that define it, right? If we're writing out a linear model, y equals ax plus b, the two things that you need to know are this a here, which is what we call the slope, and this guy here, which we call the intercept. If you know the slope and the intercept, then you know the entire linear model, right? Those two features, the slope and the intercept, define a linear model. So, how do we actually find that slope and intercept? Well, luckily, when you do that lin reg ax plus b, that same feature that allows us to calculate the correlation coefficient, this gives both the slope and intercept. So we don't need any sort of special extra feature. We can continue to use that sort of lin reg ax plus b function on our calculator to calculate both the slope and the intercept. So let's go back to our example and actually do that, and then see that that model really does fit our data. All right. So we still have this sort of information. You should still have the data in your calculator here. Let's go ahead and determine the LSR here. So let's determine the LSR. So what we're going to do is we're going to run that, we're going to run that lin reg ax plus b again. This time, right, we're not going to record the r value because we already did that. Instead, we're going to record that a is negative 4.4 and b is going to be 18.5. So this gives us our LSR here as y equals negative 4.4x plus 18.5. So this right here is the LSR. Now, in algebra, this is a totally fine presentation. X and y, very standard for algebra. But let's remember what x and y represent for us. Well, y, that's your dependent variable. That's your response variable. So when we have this model here, we're saying that the months is actually equal to negative 4.4. Our x variable, right here, is our independent. It's our explanatory. So that's times the GPA plus 18.5. And to me, right, while this is a fine presentation, this is an even better one because this reminds us that these were our variables, right? This also sort of indicates how we would use this model. If we know somebody's GPA, we can plug it in right here, multiply it by negative 4.4, add it to 18.5, and then that'll tell us about how many months it should take for them to get their first job. All right, we're doing a lot of stuff right now on sort of faith in the calculator. Let's actually see if this LSR really fits the data we have. So what we're going to try to do is, as one last thing here, we're going to try to draw LSR on our scatter plot. Now, how do you draw a line on a graph? Well, you're going to need 2 points. Anytime you want to draw a line, you need 2 points. So we need 2 points. Well, you can use any 2 points you like. But if you think about it, you're going to be drawing it on this graph. So you wouldn't want to choose like an x value of, 5, because that would be over here. That wouldn't make any sense. You wouldn't want to choose an x value of like 1, because that would be somewhere smushed in there. Instead, you'd want to choose x values in the sort of range that we had. So out of convenience, what I always do is I always use where I started my axis and where I ended my axis. So let's do that. So let's choose x equals 2.8. How do we get the y value? Well, we plug it into our model here. So if we do x is 2.8, then y will be negative 4.4 times 2.8 plus 18.5. And if we calculate that, that would just be on the calculator. So just negative 4.4 times 2.8 plus that 18.5. It looks like we'd get 6.18. So our first point, and we'll do this in just a little bit of a different color, is going to be 2.8 and 6.18. So let's go ahead and calculate another one, and then we'll go ahead and draw it onto our graph. So let's choose another x value to get a point. And we said that we would take the other end of our axis, so that 4.0. So let's choose x equals 4.0. And we do y equals negative 4.4, 4.0 plus 18.5. Once again, just do that on your calculator, negative 4.4 times 4.0, and then add that to 18.5, and you should get 0.9. So that means our sort of second point is 4.0 comma 0.9. All right, let's go ahead and draw those points out. And again, I'll continue to use this sort of blue color here. So 2.8 and 6.18 would be somewhere like right about there. And you'll notice that I'm also trying to put a little star notation there, right? Not like a dot to sort of separate it, that that's not a data point. That's something that our model is predicting. Then we also have 4.0 and 0.9, so that would be somewhere right there. And let's go ahead and actually draw the line that would connect those 2 points. So trying to do that as straight as possible. There we go. And what do we notice? Well, we notice that that line really does go right through the sort of middle of our data points. You'll notice that some of the data points are above that line and some of the data points are below that line. But overall, the line tries to estimate the general pattern of the data. And in fact, mathematically, this is the best fitting line that we can fit to this pattern of data. We're going to study this regression line, this least squares regression line, a lot more. But a couple things to just keep in mind. These points that we did here, they're just completely made up. We chose 2.8 and 4.0, so they would be nice and easy to draw it on here. But they do mean something. This 2.8 and 6.18 tells us that we predict that someone with a 2.8 GPA should take about 6.18 months to get their first job. And this tells us that somebody with a 4.0 should take about 0.9 months to get their first job. Now, you'll notice that certain people, all these people here, took longer than predicted, and all these people down here took basically shorter than predicted. So again, our predictions aren't saying that they'll be true for everyone, but they're going to be true sort of on average, right? They're going to be sort of generally true about the relationship that we're seeing here. All right. We'll learn how to measure how good our sort of predictions are in the next video, and we'll talk a little bit more about building these LSRs and understanding the components of the LSR. For now, though, that's going to do it for this video, and we'll be continuing on with the least squares regression line in the next one.